is how you control the robot. So how do you make a robot do what you want it to do? With open loop, there's no feedback. And then with closed loop, there is feedback. So here's open loop. We just have input to controller, to control signal, to robot out. So using the RC car example, you have the person input to the joystick, sends a voltage to the car, and the car moves. Now closed loop is with feedback. So you use a sensor to close the loop. And the control, what goes into the controller is actually the error signal. So it's the input minus the output. This is called a negative feedback system. So you take the input, you see how far you are away from it actually, and the error goes into the controller. Now, an example of this one would be cruise control. So you have your input would be desired speed. Actually, let me show that picture. Okay, so here you have desired speed, and then that goes into a controller circuit, but it's subtracted is the actual speed. So desired minus actual, that goes into the controller circuit. And so then the cruise controller sends the signal to the car, which spins the wheels and moves the car forward. The speedometer looks at what is your actual speed, sends that back in so the controller can tell desired minus actual. So this is a closed loop system. The difference between open and closed is you have a sensor there that closes the loop. Okay, so moving back here, we design a controller to compensate for the robot's internal dynamics and achieve the desired trajectory. So the controller here has to make up for the actual robot. Maybe it's heavy or it has friction or whatever. It doesn't do exactly what you want it to do just based on the input. So you need to put in the controller. Use whatever sensors are necessary to compare output to input. So if your desired position is in meters, you'd use an odometer. If it is an angle, you'd use an encoder. Just whatever type of sensor you need, that's what you put to close the loop. Now the transfer function relates the output to the input. It is the impulse response function because it shows how the system behaves for a given input. So you find it using algebra. That is specifics on how I got these two things are in the notes. So they multiply in series, add in parallel. G represents the transfer function. So if they multiply in series, then here we have a GC. So controller transfer function times plant transfer function equals the open loop. The open loop transfer function would just be this thing if you didn't have that feedback line. So to get the closed loop, it's this formula, and I worked out in the notes, they're on D2L, it's called Chapter 6 Controls Notes. That shows the algebra of how I got this formula. And this system is called negative unity feedback because it takes the output and it doesn't do anything to it. It just changes, like there's no change from that output until it goes in here. So that's where the unity comes from, and then the negative sign is right there. So negative unity feedback when there's no transfer function box down here. So there's kind of two parts to the problem solving with this. For system modeling, you start out in the time domain, because that's real life. So we're over here in time domain. Draw the free body diagram of your system with all the forces on it and derive the dynamics equations. So that is in the time domain. You'll get the force, position as functions of time. So then you move to the frequency domain. And this is a domain where math is easier, but it's not real. So we have this fake variable, the frequency variable S, which represents a derivative. We write all